Hi, this is Andrea Vitrone, Lab M04, and this is the ninth lab, the oscillating spring. The problem of this lab is to examine the motion of a spring mass system where a mass swings in an arc while oscillating on a spring. So this is different from earlier labs because it's not just going up and down, the mass is also going side to side as it goes up and down. We had to use the tracker data to correctly predict position using VPython, find the period of oscillation in the x and y directions, and apply the energy principle with the momentum principle, as well as predict any changes from moving the origin. And those are part of the what does it mean questions. The result is that the computer model successfully predicted the position of the mass using a combination of the momentum principle and the energy principle. For question 2, does the video identify the model as relevant to the physical system? We want to look at tracker. So here is the system that we have going. It includes the mass and the spring. The spring starts here and goes down here. And the mass, it weighs 0.402 grams. And the length here is 0.7 meters. And I used the calibration stick to do that. These are the points as the mass changed over time. And over here you can see the change in the x direction over time and the change of the y over time. And the period of oscillation is from the top of one to the top of another. Down here you can see the data points that I copied and pasted, and I used the initial conditions of 0.57 seconds and the x and y values for the VPython code. This is my computer model. My initial conditions are here, the ball's mass, and the position and the velocity in the initial time, which I got from Tracker. And then I have a few other initial conditions of the K constant from the spring from a previous lab, and the compression of 0.127 meters. Here I calculated the potential gravitational energy, which is MGH, or mass of the ball times 9.8 times the change in height, which is the ball's position in the y direction. The kinetic energy I calculated by doing 1/2 mv squared. Here I found the force of gravity and the force of the spring to get the net force, which I then used in the momentum principle, or the change of momentum equals F net change of t, or change of time, to update the ball's velocity and update the ball's position. This is a comparison of the code from the computer model, which is right here, and the tracker data over here. So as you can see, the motion of the path of the mass is very, very similar. So that brings us back to the third and fourth questions. Connecting the model to the experimental data, which I just showed you, and then the comparison between the mass's position in each of the models. So for the tracker, at 5.03 seconds, the x position was negative 0.03645, whereas in the code from the computer model, at 5.035 seconds, which is close to 5.03, the position in the x direction was negative 0.0365. So those two are very, very, very close. And in the y direction, it was negative 0.641, whereas in the computer model, it was also negative 0.641. Therefore, I can conclude that the computer model did actually predict the position of the mass correctly. Finally, I'm going to talk about the what does it mean questions. I calculated the period in the x and y directions using two different equations. For the x, it was 2 pi times the square root of the relaxed length of the spring divided by 9.8. For the y, the period is 2 pi times the square root of mass divided by the K constant. And I found two different times here, 1.6 and 1.1, so that shows that the periods are not the same. Next, I concluded that the work done by the surroundings on the system was 0, and you can see this because according to the energy principle, work equals the change in energy of the system. And when I plotted the change in energy of the system, which is this blue line right here, you can see that over time it stays very consistently at 0. So that shows there was 0 work. Also, this is another comparison right here of the experimental and the computational model, and you can see that the position over time is very, very similar. For the final question, by changing the origin of the axis, only the gravitational potential energy is changed because gravitational potential energy is mgh, and changing the origin will change the height. The kinetic, however, will not change. Thanks for watching!